Hi everyone! Welcome to our April 1st and April 2nd Recursion Recitation worksheet. Recursion is a topic that is more complex when it comes to this class, so we have a lot of materials to help you completely understand this. We have 2 different videos on our YouTube channel, as well as other opportunities to get help within office hours. Alright, well with that, let's get started. So what is a recursive function? So we know that a recursive function is any function that calls itself. So what this means is that from within one function, there is a recursive call to the same function that it is in. Okay, so what are the 3 main parts of a recursive function? So we know that the first part is a base case. A base case is what allows us to terminate the recursion. So this base case could be anything from an empty string or some sort of other thing like an empty dictionary or the length of a string equaling 0. With this, we also have a recursive step. The recursive step is what makes the problem approach this base case. So in this case, this could be either shortening a string or iterating further through the list. Finally, we have what we mentioned before, the recursive call. This is what runs the entire recursion. So this is the function that actually calls itself. It may be helpful to think of the base case in recursive step similar to how we've thought about while loops. While something has not happened or while something is happening is similar to the base case. So whenever I have not reached an empty string or have not reached an empty list, I want to keep going. But within the while loop or within the recursion, we also have something that makes it eventually stop. So what we have here with the recursive step allows us to eventually make it to the base case, so the recursion doesn't occur forever. Just like we have something in our while loop that continually makes the while loop untrue up until a point.
Alright, so before we go ahead and do some coding examples with recursion, we thought it would be a good idea to actually trace through some recursion first. But before we even start tracing, I sort of wanted to draw attention to something back from Unit 1. So you may remember seeing a circumstance like this. You've got one function up here, then you have another function down here that calls another function. So let's go ahead and say that we made a function call to this guy right here. So, down here, I made a function call, okay? So I'm going to go into func, and then Python sort of reads the same way that we do. So it's going to go line by line, and every time it finds something that it doesn't recognize, it has to go look it up. The same way that we read books and then, we find a complicated word, we got to go into a dictionary to look up what that word means before we can continue. In this case, the complicated words are other function calls. So Python's going if test. Well, here's the thing. Python has no idea what test is. So in order to figure out what it means, it has to go run this function. So everything in this execution of function stops for a second because Python is now focused on this. It's going to go up here, it's going to run test. In this case, all test does is returns 5. So we're just going to say, now it knows what it means. So if 5 equals 4, well, that's not true, so it doesn't do anything in here. Then when it gets down to this, Python's memory ain't that great. So it's got to go ahead and run it again. All right, so once again, if test, it's just going to stop the current execution of func. Everything's on hold until it can come back and find out what test equals. And in this case, just same old, returns 5. If 5 equals 5, return yay. So the main point that I'm trying to get across is that the same idea applies in recursion. Every time you make a recursive call to the function itself, the current execution of that function pauses until we move on and figure out the one before. So it isn't uncommon to have several executions waiting on other executions. And we'll see more of what I mean when we trace through this example. So with that out of the way, let's go ahead and get started. So we're going to do this with the context technique. That's not like an actual thing or anything, I just call it that. But basically how it works is we write down wherever we left off each time we have to pause our current function to make another recursive call. It's easier to show and tell, so let's just go ahead and get started. So first step, no matter what technique you use, is I like to identify the base case. And the base case usually sticks out to us because it doesn't have any real logic involved. There's no recursive calls or nothing. It's just a stagnant value that is told to us or given to us through some other logical process. In this case, I'm noticing that this particular block right here has no dependency on a recursive call, right? This one down here, you need to make a recursive call here. Same for this one. Up here, it's just if num is less than or equal to 2, return an empty list. So let's go ahead and just keep note of that. So that right there is my base case. And if you're ever coding a recursive function for this class, just remember, you can get points just for having the correct base case. It's always a good thing to keep in mind. Now that we know our base case, let's actually execute this function. So where do we start? Start with the function call. And our original function call is recur of 5. So with the context technique, every time you make a function call, I want you to write down the function call that you made with a line under it. So in this case, I made recur of 5. So let's just write over here, recur of 5. Okay? Now, just run this how you normally would. We're going to substitute 5 for wherever we see num. So if 5 is less than or equal to 2, it's not. If 5 squared is greater than 16, well, 25 is greater than 16. So I'm going to be focused on everything going on in this block right here, okay? So a list equals recur of 5 minus 2. So a list equals recur of 3, right? Now here's the thing. At this point, Python has encountered something it doesn't know, so it's going to already pause recur of 5. However, for our bookkeeping purposes, I'm going to write down the rest of the stuff that's inside this if block, just so it's easier for me to keep track of when I come back to it. So notice, we're going to write down these two lines. alist.append num times 2. So, and for ease, I'm just going to call num n. And then I'm going to return a list. Great. Now remember, none of this has happened yet. Just this. We're still stuck here. So now let's draw an arrow. So our next call, function call, is going to be to recur of 3. So I'm going to write that down. Okay? So start over from scratch. We don't have to keep track of anything else. I'm going to erase this because we're not focused on that anymore. Recur of 3. If 3 is less than or equal to 2, it's not. If 3 squared is greater than 16, 9 is not greater than 16, then we're going to focus on this block down here. A list equals recur of 3 minus 1. So, as usual, write that down. 3 minus 1. And then remember, at this point, we've paused this execution. But I'm still going to write down the other stuff so I can keep track of it. So what else? A list dot append num, and then return a list. Okay. Now I draw my arrow to recur of 3 minus 1, 2. And now, when I run recur of 2, if 2 is less than or equal to 2, it is return empty list. Great. So at this point, I've reached my base case. I don't need to make any more recursive calls. Now the nice thing about the context technique is anywhere I see recur of 2, I can substitute it on my way back up. How it's going to work from here on out is we're going to sort of start going back up this chain. So we went down to the base case, it's time to come back up. So to do that, let's go ahead and sort of translate all of this. Let's finish this execution, because now this execution is done, recur of 3 is unpaused, let's continue. So a list equals recur of 2. Well, we know recur of 2 is an empty list. A list equals empty list. But then a list dot append n. So what's n? this helps us keep track of what our params are. So in this case, it's 3. So I'm just going to go ahead and throw 3 into this list. Okay? And then I return a list. So my overall value for recurve 3 is that, just a list containing 3. So now wherever I see recurve 3, I can substitute this value. So a list equals recurve 3. Well, great. I have the answer to that question now. A list equals 3, right? But then I'm appending to this a list dot append n times 2. So what's my n this time? It's 5, right? So let's go ahead and tack on a 5 times 2, or a 10, onto this list. And then I return a list. And now we don't have anywhere to go back up our chain, right? So at this point we are done. We have figured out the full value of recur of 5, so our final output is going to be 3, 10, okay? It's a list containing that. So that is how we like to approach recursive functions. It's very important to have good bookkeeping on your way down until you find the base case, and then it's really easy to work your way back up if you've kept track of wherever you were in the function. All right, so now let's go over a case where we use the stack technique. Before we go into it, let's think of an analogy. So I like to always think of a can of Pringles, okay? So you've got your can, right? And then you've got a bunch of chips inside the can. I'm a fantastic artist, as you can see. So in order to get to this bottom chip, you have to remove all the chips above of it. So in order to get to this chip, for example, you need to remove the chip directly above it, and so on and so forth, right? So if this is a full can, you gotta start by removing the chip at the very top. Well, let's go ahead and reuse this analogy for a recursive function. So in a recursive function, remember how we kept on pausing the current execution in order to complete another sub-execution? So if we made a recursive call, we had to finish that recursive call before we could finish our overall function. It kind of works the same way as the chips. So in this case, the bottom chip is always going to be that first function call that you made. So in this case, it would be like foo of 3, all right? So this bottom one right here would be foo of 3. And then every time you make a recursive call inside of foo, or inside of foo of 3 specifically, you have to finish that recursive call before you can finish foo of 3. So in that case, you'll get more added on top, and more, and more. Now, the only point where you stop adding these chips is when you reach the base case, right? So once you reach the base case, so in this case, let's say it's something. Once you reach the base case, you can start removing the chips out of this stack, right? Until you remove this last one, and then you're done, okay? So in this case, just remember, bottom chip is where you started, and then the top chip is the base case that we're heading to, all right? It's a good analogy to think of, and with that, let's go ahead and get started with the stack technique. So to do the stack technique, draw a stack, okay? So there's my stack, very even. And as I said, we're going to put in our function call. So in this case, my first function call is to foo of 3. So that'll be my very bottom chip, okay? So foo of 3 goes there. Now let's go ahead and start running these functions. So if 3, remember 3 being num, so if 3 is equal to 0, return 1. So this right here is obviously my base case because it doesn't make a recursive call, just returns a value. Since I didn't hit the base case, I have to make a recursive call. So return 3 plus foo of num plus 1. So let me add the 3. All right, so now I've got to figure out what 3 plus foo of 4 is, 3 plus 1, right? So now basically what I got to do here is I have to execute foo of 4, all right? So If 4 equals 0, it doesn't, then I have to return 4 plus foo of 4 plus 1, so 4 plus foo of 5. 4 plus foo of 5. Now, you may have caught on at this point that it doesn't look like we're going to be heading to 0, or our base case, anytime soon, right? So that leads me to believe that we have a problem. We have reached infinite recursion. We are never going to hit our base case. And this has a very specific name, and there's a reason I use this example with the stack technique. This is called a stack overflow. It's like if you had your Pringles can and you just kept on adding chips even past the capacity of the can. In this case, you're going to keep on adding too many chips, the whole stack's going to overflow. And the reason why it's called a stack overflow is because your computer has a recursive stack capacity inside of it. It'll only execute so many recursive calls before it's detected a problem, at which point it'll say this is an error. Okay? So in Python, I believe the specific error that it spits out is max recursion depth exceeded. So the reason why, once again, is that you did not make a step, you did not have your recursive step towards the base case, okay? And if anything, we were actually moving away from the base case. So there's two ways that we can resolve this problem. The first thing is we can start from a negative number, because if we started from -3, for example, if we kept on adding 1, we would eventually hit 0. However, let's go ahead and rewrite our function to actually move towards the base case. All right. So to do that, instead of having it add 1 every single time, let's just go ahead and make it subtract 1. Okay. So as soon as I delete this, all right. So now let's go ahead and do that problem again. So draw my stack. And in this case, I'm not going to have it be +1. I'm going to have it be -1. Okay, so let's start with foo of 3. So I'm going to put that in my stack. Foo of 3. So if 3 equals 0, it doesn't return 3 plus foo of 2. Okay, so I need to figure out right here 3 plus foo of 2. All right, so let's run foo of 2. If 2 equals 0, return 1. Well, it doesn't. So otherwise, return 2 plus foo of 1. Okay? Return 2 plus foo of 1. All right? Now let's run this again with 1. Well, 1 equals 0, it doesn't. Return 1 plus foo of 0, right? 1 minus 1. So here, return 1 plus foo of 0. Okay? So foo of 0. If 0 equals 0, here it does. So now I've reached my base case, or my top chip, okay? So 1. And now I can start working my way back down the stack, okay? So foo of 0, so this I can pop off, all right? So now 1 plus foo of 0, that's 2, right? Great. Then 2 plus 2, that's 4, right? Then 3 plus 4, 7, okay? And then that means my final answer for this is 7. So overall, the value of foo of 3 should be 7, okay? So notice this wasn't so bad when you're doing the stack technique because there's not a lot of bookkeeping going on. When you need to keep track of a lot of variables or there's different if-else statements and stuff like that, I strongly recommend using the context technique just because it has more flexibility in how much you can write.
Alright, now let's get into some actual coding. So we're going to write a function called reverse, which takes a string and returns the reverse of the string using recursion. So let's start out with defining our function. So define reverse, and I know that I'm going to be taking in a string, so I'm just going to call that aster. Perfect. So the first thing I need is a base case. I know that I want to keep having recursion happen until I get to the very end of my string, because at that point there's no more to add to the end. So my base case here is going to be if the length of my A** equals 1, then I'm going to return A*. In this case, I could also do if the length of my A* equals 0 and return A*. In this case, we're just go ahead and adding the very last letter to it to the end. Okay, now let's look at our recursive step and recursive call. So what is happening here? I know that what I need to add is the very last letter to the beginning of my new word. So I'm going to have return A* -1, because I know that that's going to give me the last letter in my A*. And what do I want to add to this? Well, this is where I'm going to have my recursive call and recursive step. So I'm going to say reverse, and now what is the A* that I now want to have in our new A*? This is where recursive step comes in. So I know that I just took off the very last letter to add to my new string. So now I want to shorten the string so that last letter is not added again. So I'm going to use A* and slicing. I'm going to say the length of A* -1 to ensure that now I no longer have this last letter that I just added here. Makes sense? Alright, let's keep going on to our next problem. In the next situation, they want us to write a function called first that takes in a string and recursively finds the first capital letter in that string. This function should return the first capital letter in the string, or none if there are no capital letters. Alright, so let's define our function. So the first thing I'm going to do is define first, and what I'm going to be taking in this case, I know I'm just going to be taking in a string, so I'm going to call it A* again. Alright, so the very first thing we start out with is our base case. So in this case, we know that if there are no capital letters, then I want to make sure that I return none. So I'm going to say, if the length of my A* equals 0, return none. Now, this base case will only happen if I keep shortening A* and I never reach a capital letter. Alright, let's continue. So what do I want to return and when? Well, what am I checking? In this case, I'm checking to see if it's a capital letter. So I can use isUpper. So I'm going to say if the first letter of my A* is upper, which will return some sort of boolean, then I'm going to return what that letter is. So this is just going to be looking from the beginning and see if that is a capital letter. Alright, well what if it's not a capital letter? What do I need to do? This is where I have my recursive call and my recursive step. So I'm going to return first, and as I just checked the very first letter and we know that that's not capital, I'm just going to chop that first letter off and say A* from sliced from 1 to the end. Alright, and there we have it. Here we look at another coding function called SUMALL. Here we're going to take in a string and recursively add all of the digits in the string. Okay, so let's start off with our function definition. So I have define sum all. I'm taking in a string again, so I'm just going to call it aster. All right, so what is my base case? Well, I know that if the length of my string is 0, then there's going to be no digits in that string. So I'm going to make that my base case. So with the length of aster equals 0, I'm going to return 0. Alright, now let's see, what am I checking? Alright, well I know that I want to check to see if it's a digit. So I'm going to say if, and I think it'll be easiest, just like we did before, to look at the first letter, or first character, and check to see if it's a digit. So we can say if aster 0 is a digit, we know that we want to return this digit and the sum of the rest of the digits coming after it. Well, we know that this character that I'm looking at is just that, a character. So we need to make sure we turn it into an int, return the int of aster 0 plus, and here we have another recursive call and recursive step. So I'm going to say plus sum all, and since I just checked the first one, I know I don't need to look at that anymore, so I can just say aster from 1 to the end. Alright, well I'm not done yet. What if it's not a digit? What do I need to do then? Well, I can just say else, sorry I'm writing small here. Well, I know that I don't need to return the int of aster 0 because it's not an int, but I still need to make my recursive call and recursive step. So I'm just going to say return sum all of aster and everything after the first digit, or first character. Alright, let's keep going. Alright, let's look at our final coding problem. We want to write a function called encode, which takes in a string as a parameter. The function should then reorder the characters in the message by taking the first character and adding it to the last character, and then adding the second character and the second to last, and so on. So that's a little confusing, but let's look at our test cases to see what this means. So in this case we have ego. We know that E is our first letter and O is our last letter. So we want to add those two together and put it in our new string, and then do that again with the second letter and the second to last letter. Perfect, GG. Alright, let's also look at pancakes. So we have P is my first letter and S is my final letter. So I have PS in my new string, and then I have A as my second letter, E as my second to last letter, so I have AE, and so on. Alright, well let's get started with our function definition. So I'm going to say define encode. Again, I'm taking an aster, so I'm going to call it that. Okay, so now let's think about what my base case is. So in this case, the only time that I want to stop doing this recursion is once the original aster doesn't have any characters left. So I'm going to say if length of aster equals 0, I'm just going to return an empty string. So this empty string here is actually going to be what we're adding the rest of our new letters to. So this is the same as like initializing a new empty string in a problem that you're using a for loop for. All right, let's keep going. So what do I actually want in this string? Well, I know that I'm going to return the first letter, so I can get that by doing a star of 0. What's the next thing I want? The last letter. A star, -1. And then here comes my recursive call, recursive step. So I'm going to say encode. And then what do I want to take away? Well, I know that I now want to look at the second letter in the second to last letter. So I can do this easily by just getting rid of the first letter and last letter. So I can say a star sliced from 1 to the length of a star -1. And this takes off our first letter and our last letter. All right, there you have it. So we're going to do a little more review on recursion just to help you with some of the common mistakes that we see and common misunderstandings.
All right, let's go over some common problems that we see, along with some good things to know when you're doing recursion. So let's go ahead and say I gave you a problem. Find the length of a string without using the len function. Okay, so that, not allowed. Okay, so let's go ahead and write our function two ways. I'm going to do it iteratively, and I'm going to do it recursively. And we're going to see if we can draw some patterns between it that may be helpful for you. So let's do it the iterative way first. It's pretty easy, right? So all we got to do is say define, I'll call my function length, takes an aster. And what are we doing inside? Well, I can just be like, first of all, I'm going to need a count variable, right? So let's just say count equals 0, and then for car in aster, I'll just say count plus equals 1. And then at the very end, return count. Now, if we wanted to do this recursively, the key thing to keep in mind is that we don't really have this sort of iteration process anymore, and we certainly don't have any count variables. The reason being is that every time we make a recursive call, count is going to start back from 0. So we can't have these values persisting between recursive calls, okay? Unless you have helper functions, which is outside of the scope of this class. So for now, let's go ahead and just see how we can approach the same function, but recursively. So define length of aster. So as I said before, what is our base case? Well, I know that if I have an empty string, that its length is 0, right? So I can just say right here, if aster equals empty string, return 0. All right, notice the lack of a count variable for the reason I mentioned before. Now, if it's not an empty string, I know that I need to start chipping my way down to the empty string, okay? So the way I can do that is, well, first of all, I know that this string, if I've made it to this return statement down here, it means I didn't trigger this if statement up here, which means I'm dealing with a string that at least has a length of 1. So what I can do right now is I can just return 1, but let's go ahead and return 1 plus the length of whatever's left in the string minus the first character, okay? So if I had a string of 1 character, for example, then I would strip away that first character and then make the recursive call on whatever's left after I took away that first character. And the way we can do that is by making our recursive call again plus length, and this time we slice away that first element of aster, that first character. And to do that, it's just a matter of aster from 1 to the end, right? So notice We did not use any count variables, no for loops, and there is no need for any values to persist between calls of length, right? Each one is independent all the way down to the base case. So a problem that you may see is that you don't want to be keeping track of things like count between recursive calls because they simply don't exist between recursive calls. You're going to get reset every single time. They're of no use to you. Another good pattern to know between these two is this is a very easy way to translate between thinking iteratively and thinking recursively. So let me label those two down. Iteratively, and then recursively. For example, if you know how to accomplish a problem using the iterative thought process, you should be able to translate it to recursion just by using some basic patterns that you may see. So for example, notice in order to go for car in Aster, so let's say if my thing was A, B, C, D, in order to jump from A to B to C to D, I had to use a for loop, right? So for car, and car is going to do the jumping. In order to do that jumping quote unquote, in recursive functions, I have to make a recursive call to the same string, but one chopped off. So instead of A, B, C, D, it goes to B, C, D, and C, D, and D, and so on and so forth until down to the empty string. So this is a pattern that you can use to your advantage. Instead of having to iterate when you're not allowed to, so if we say solve this problem recursively, it means you do have to do it recursively. Instead of using a for loop, you can just know, okay, I'll just make a recursive call to the same variable but with one of the elements chopped away. Same thing applies for lists. If you need to look through every single element in a list, you can make a recursive call to that list but with the first element removed. So that's a helpful tip in terms of translating between the two. If you can solve the problem iteratively, or at least think about how to solve it iteratively, you can translate it to a recursive thought process. So hopefully that helps you out on the test.